I welcome you all once again to the previous year sessions which we solved questions from flight and space mechanics in the year 2013. So today we'll be focusing on that. My name is Praveen. So and today, like I said, we'll be focusing on the questions asked in the year 2013 in the area of flight and space mechanics. Okay. So let's get started with the first question. So before going into that, quick details like as usual emphasize the number of 1 mark questions were asked is 5 in total, and the number of 2 marks were asked are 7 in total, so totaling to 19 marks. Oh, again, so the range is maintained, so 16 to 25 marks is what they will prefer. Okay, so let's get started with the first question of today's session. So take this problem: which one of the following is the most stable configuration of an airplane in roll? So we have 4 options: sweep back, unhedral and low wing, sweep forward, dihedral and low wing, sweep forward, unhedral and high wing, sweep back, dihedral and high wing. So just underline this word: most stable configuration of an airplane in roll. Okay. So let's look at the basic theory behind the stability. So let's say a low wing, this is basically an unstable case. Okay. And how do you stabilize it? By adding a dihedral. Okay. Dihedral is basically this angle. Okay. So this is basically a stable aircraft. This aircraft, this is stable aircraft. Whereas a high wing is a stable one. Okay. This is a stable aircraft. If I provide the same up angle, that is the dihedral, it will become more stable. More stable related to this thing. Okay. More stable with respect to this. Okay. Whereas for high wing, this is again stable aircraft. Let me just reiterate on the point. So if I try to give a low angle like this angle is called as an unhedral. Okay. This minus gamma. This is an unhedral angle, and this is a dihedral angle. So then what happens is your stability is lowered, which means what? Now you are able to control the aircraft. There is basically a trade-off. Controllability is achieved. So which means a high-wing aircraft with a dihedral angle will be the most stable one. This case is the most stable among all of them. So now if I go back to the options that are given there, so which means I can see here. So my dihedral and high wing, So we have 2 options: dihedral and high wing. Okay. Right. So let's look at these two: sweep forward and sweep back. Okay. Again, from theory, just give me a second. Because I just want to turn on the live session. Okay. Right. So coming back to that. So sweep. So what is sweep is basically, instead of having a rectangular wing, so you will have a sweep angle like this. Okay. So this is basically a, let's say, some angle delta. So this is basically sweep back. Okay. So when you sweep back the aircraft, when the wings are swept back, when the wings are swept back, your stability improves. That is the lateral stability. Okay. Or the roll stability. Okay. The lateral stability or the roll stability increases. Whereas, when you provide a sweep forward, which is like this is some minus delta. That is basically destabilizing. Okay, so which means my sweep back has to be the stable case. So if I go back to the options, so this has to be the sweep back, dihedral, and high. Okay, so this is the most stable one. Hope you guys understood. Okay. right? Okay. So if no doubts, if you have any doubts, please feel free to put it in the chat box. I'm here to help you. Okay. So let me go to the next question. Which one of the following flight instruments is used on an aircraft to determine its attitude in flight? So we have four options: vertical speed indicator, altimeter, artificial horizon, turn bank indicator. So underline the attitude, okay? So simple difference, okay? What's the difference between altitude and altitude? So altitude is basically the height, okay? Whereas attitude is basically the orientation of the aircraft with respect to some reference plane, okay? Of the aircraft and attitude is orientation of the aircraft. So which means vertical speed indicator, the name says it measures the speed, so this can't be true. Altimeter, which measures the altitude, so this can't be true. Artificial horizon and turn indicator seems close, but let's see. So vertical speed indicator is used to measure, your sink speed or the rate of climb. Okay. Altimeter is used to measure the altitude. Okay, as the name suggests. Artificial horizon is used to measure the altitude. And turn bank indicator, because it measures the bank, so it's basically measuring the angle of bank. And turn. So which means my answer has to be C. Okay. So the artificial horizon, is basically measuring the altitude of the aircraft. Okay. Okay. So if no doubts, then let me go ahead. Next question. A supersonic airplane is expected to fly at both subsonic and supersonic speeds during its whole flight course. Which one of the following statements is true? So we have four options. Airplane will experience less stability in pitch at supersonic speeds than at subsonic speeds. Airplane will feel no change in the pitch stability. Airplane will experience more stability in pitch at supersonic speeds than at subsonic speeds. And pitch stability cannot be inferred from the given information. So it is saying that it is expected to fly at both subsonic and supersonic speeds. Okay. So let's see. Okay. So let's say you have an airfoil. Now you will have some, let's say, some marks number, free stream mark number of 0.3. So you have your aerodynamic center in here, right? So there will be some lift pressure distribution, which obviously if I draw this plot, if I am correct, okay. Something like this. Okay, it starts from minus CP versus X. Okay. Starts from -1. Okay. Right. So let's say that I increase the Mach number. Okay, we have to understand what happens. If we increase the Mach number. So if you refer to aerodynamic theory, it states that increasing Mach number or increasing the speed basically pushes the aerodynamic center back. Okay, so which means the aerodynamic center will move back. Which means what? If aerodynamic center moves back, your neutral point will also move back, right? Because neutral point is same as aerodynamic center, but viewed in the stability aspect. So if neutral point moves back, what will happen to the static margin? Static margin will also increase. If static margin increases, then what can we say about the pitch stability? It increases, right? Which means what? If I go back to my option, so if I increase the speed, so there is more stability at supersonic speed. So it means the answer has to be option C. Okay, guys. Hope you guys don't have any notes. Let me repeat again. If you recall your aerodynamic theory, you have this aerodynamic center, which is affected by the location of the aerodynamic center is affected by the upstream conditions, right? which means if I increase the flight speed, AC moves back, so which means your neutral point moves back, so which means your static margin increases, where the definition for static margin is what? If I write it in brackets, it is xnp bar minus xcg bar, okay? Because this increases, so static margin is basically minus dcm by dcl. If static margin increases, this also increases, hence, basically, stabilizing at supersonic flight speeds, okay? Hope you guys don't have any notes, right? So if no doubts, then let me go ahead and please, like this session and share this session to your friends so that they might also benefit from this. Okay, right. So let's go to the next question. Which one of the following is favorable for an airplane operation? Tailwind in cruise and headwind in landing. Tailwind both in cruise and landing. Headwind both in cruise and landing. And headwind in cruise and tailwind in landing. Okay. So let's see. Pretty simple. So headwind is basically, so there are three winds, in aerospace literature. We have headwind, we have tailwind, and we have crosswind. So headwind, it's now, let's say an aircraft is like this, flying. Let's say it's starting to take off from the ground. Headwind is the one, that basically, it basically approaches the aircraft, It's basically the wind that is moving against the aircraft, and it basically flows over the airfoil, so which basically generates the lift. Okay, basically opposing it. You can think of like a gust of air molecules, coming and hitting the aircraft. Okay, tailwind is basically wind coming and approaching the tail like this. Okay, this is the tailwind. Crosswind is basically a wind coming in this way, the side slip plane. Okay, so basically, when you have a tailwind at, let's say, some cruise flight, this tailwind will basically increase your effective velocity, right? So basically, try to push you, So which means you will fly at a much higher speed, which means you can cover the same distance within a short span of time, right? So that is basically the effect of tailwind, right? So which means we need a tailwind in cruise, right? That's one thing. So tailwind is needed in cruise. That's one thing. So underline this. And what about the headwind in landing? Okay. So imagine while at landing, you say tailwind is coming, so which means what? Instead of aircraft now landing properly, it will come in like like a rock, falling like a thud, or it will basically again take off instead of landing. So that's not the undesirable case. So what you should do is you should have headwing such that the wind coming in basically opposes the most of the aircraft, right? So headwind and landing is again preferred. So the answer has to be option A. Okay, that is my point. Yeah. So hope you guys don't have any doubts in this, right? If you have any notes, please feel free to put it in the chat box, guys. Okay. And if you, like the session, please like it and subscribe to IGC classes. Okay. Right. So let me go to the next question. Which one of the following is true with respect to the Phugoid mode of an aircraft? So we have four options. Frequency is directly proportional to flight speed. Frequency is inversely proportional to flight speed. Frequency is directly proportional to square root of flight speed. Frequency is inversely proportional to the square root of the flight speed. So, if you recall the Phugoid formula that I gave you in the previous sessions that I conducted, so let me write down the result again. So please go back to my previous recorded lectures. You can find it in 2010 or 2011 previous questions. Where in which I wrote this formula. So this is basically the expression for the Phugoid mode. Okay. And what does this give? This basically gives the frequency of the oscillation. Okay, so this basically is an undamped motion. So from here we can see that the frequency is inversely proportional to the flight speed, right? This is an important thing. So bracket this, so which means if I write it over here, frequency is inversely proportional to flight speed. So this is my answer. Okay, pretty simple stuff, isn't it? Okay. So if no doubts, then let me go to the next question. A glider is launched from a 500-meter high hilltop. Following data is available for the glider. Zero lift drag coefficient CD0 is 0.02. Aspect ratio is 10. And Oswald efficiency factor is 0.95. The maximum range of the glider in kilometers dash. So let's do this pretty simple problem again. So let's write down the data. Let me write down the given data. He says it's launched from a height. Let's say height is 500 meter, and he's also giving CD naught, aspect ratio, E, everything is given. So maximum range of the glider. Okay, so to determine the range, so there is this formula. Maximum range is basically h into the L by D max. Okay, lift to drag ratio at maximum value. Okay, so this is the formula to determine. So which means I have to determine the L by D max. Okay. And how can I do that? Again, if you refer to, I will guide you to this book on airplane performance and design by J.D. Anderson. Okay. Please refer to this book. The formulas are available there, and derivation is also available, so you can just have a look at it. So L by D max is basically, it's given by 1 by 2 under root of K CD naught. Okay. So if you simplify this and substitute it over here, so which means my R max, is simply H is what? 500 times divided by 2 times under root of K is what? Let's keep K as such. Let me write on the K here. It is 1 by pi EAR. So this is basically, 1 by pi into 0.95 times the aspect ratio. And if you substitute the value in here, K times 0.02. If you simplify this, you will get a value, closer to 9.65 kilometer. Okay. I leave the simplification to you. Okay, the steps are this. Okay, just very easy problem. Yes, guys, simple, isn't it? Like I said, all you need is just an aptitude for solving problems. Okay, once you have that, then you would have gained the knack of solving more and more problems with the difficulty ranges. Difficulty of varying orders. Okay, that's what I'm trying to say. So mostly, questions in performance and stability, it would either involve you to use two formulas or three formulas. So what I would do is prepare a formula sheet by yourself and start revising the formulas. Okay, now is the time to it's because the D day is nearing, so you have to revise your formulas repeatedly so that you don't forget it, right? Okay. So if no doubts, then let me go on to the next question. Which one of the following criteria leads to maximum turn rate and minimum radius in a level turn flight? We have first option, highest possible load factor and the highest possible velocity. Lowest possible load factor, the lowest possible velocity. Highest possible load factor, the lowest possible velocity. Lowest possible load factor and the highest possible velocity. So because there are words, big words, so let me write the options in simpler form. So it's basically N max and V max, and this is N min and V min. Then he says, N max and V min. Then he says N min and V max. Where N and V, obviously from the naming convention. Okay. So maximum turn rate, and minimum turn radius. So let's write out the expression for the turn radius first. So R is equal to V square by G under root of N square minus 1. Okay, this is the expression for the turn radius. And what is the omega expression? It's basically V by R. So if you divide, you will get G under root of N square minus 1 by V. So this is basically turn rate. And mind you, these formulas are only applicable for a level coordinated turn. Okay, this is an important thing. So please don't apply this formula in a pull up or pull down maneuver because again you might get erroneous results. Okay, so please be wary of that, right? So in here, if you see, omega increases when your n increases as a direct dependence, and it is inversely related. So I can write it down. Omega is proportional to L, inverse proportional to V, and similarly, R is proportional to V and inverse proportional to N, right? So which means if I go back, he's asking maximum turn rate, right? So which means max turn rate. So this has to be max, this has to be min, and minimum turn radius, right? So which means if this is minimum, This is minimum and this is maximum. So both of them agree, right? So which means what? I should have a high load factor and low velocity, right? So which means option C is the correct one. That's the pointer. Yeah. So option C is the correct one. Okay, guys? Pretty simple, isn't it? Like I said, no, all are basically formula substitutions, okay? Nothing complicated comes in. Please feel free to put questions in the chat box, so that you understand. And that helps me to improve on this, right? Okay. So let's go to the next question. Consider an airplane with rectangular straight wing at the dihedral angle of gamma equal to 10 degree. Lift curve slope of the wing airfoil section is CL alpha is minus 5.4 is equal to, it's not minus, is equal to 5.4 per rad. Then roll stability derivative in per radian is dash. Okay. So it's again a direct substitution formula, which means CL beta is minus 2 beta. So it's not minus beta. So just erase that. It's minus 2 gamma S gamma y bar by SB dou CL by dou alpha. Okay. Where this is my lift curve slope and this is my dihedral angle. So if you substitute the values, which means what I will have minus 2 into 10 degrees. So multiply this by pi by 180 so that you will get the answer in radians. S gamma by S. Okay, so which means rectangular straight wing. Okay, it's what is given. Okay, so let's consider the wings like this. Let's say the fish is like this. S gamma is basically the area of the half one of the dihedral wing, right? So S gamma by S, this is basically total. So this has to be 1 by 2, right? From the given information. And Y bar by B. Where does your net force act? Let's say it acts at the centroid of the wing, right? So if you keep this as Y bar, okay, so which means what? This is, again, B by 2. So Y bar by B will give you a 1 by 4 factor times you will have a dou CL by dou alpha, which is 5.4. If you simplify this answer, so mind you have minus sign. So this will turn around to be minus 0.2356. Okay, so this is the answer. Yes, guys, hope you guys understood this. It's pretty simple. Yes, so again, let me repeat. So have a direct formula as 2 gamma S gamma y bar by SB dou CL by dou alpha, which is the lift curve slope of the wing. And now substitute the values, you get the roll stability derivative. Okay. Right. So let me go to the next question if no notes. So data for an airplane. It's a common data link question. Data for an airplane are given as follows. Weight is 30 kilonewton. Thrust available at sea level is 4000 newton. Wing platform area is 30 meters square. Maximum lift coefficient is 1.4 and drag coefficient is 0.015 plus 0.024 CL square. Assume air density at sea level is 1.22 kg per meter cube. Stall speed of the airplane is, we have four options: 17.36, 34.22, 45.52, 119.46. Okay. So let's try to do this. Pretty simple. So what is the stall speed formula? It's again direct thing, We know that V is equal to under root of 2W by rho SCF, right? And where does the stall speed occur? Stall speed occurs when the lift coefficient is maximum, correct? Maximum. So which means if I just substitute that over here, so which means my V stall would be under root of 2W by rho S CL max. Okay. So what is my CL max? It is given, if I go back to the data, it's 1.4, right? Substitute all the data that you know, which is under root of 2 times weight of the aircraft is 30 kilonewton, right? By rho is 1.22 times the surface area is 30 and CL max is 1.4. So if I simplify this, you will get a velocity close to 34.21 meter per second. So this is my expression for the V stall, okay? The stalling speed. Hope you guys don't have any doubts in this. So if you just write it over here, option is answer, option B, okay? Understood, guys? Pretty simple again, isn't it? Direct formula substitution. That's what gate tests you, okay? How effective you know the formula and how do you know to apply the concepts at relevant places, right? So let's go to the next question. We still have three more questions. Again, for the same data, the weight is 30 kilonewton, thrust available is 4,000 newton, wing platform area is 30 meters square, maximum lift coefficient is 1.4, drag coefficient is 0.15 plus 0.024 CL square, and the density is 1.22. Minimum and maximum speeds of the airplane in level flight condition at sea level are. So this is, I think, a pretty big problem, lengthy one. So let's do this, okay? Again, it's a simple thing. So we know that at level flight, level flight. So what is the balance condition? Lift equal to weight and the thrust equal to drag, right? So which means I can write the thrust equal to drag as weight by CL by CD, correct? That's what I can do over here, right? Which means if I rewrite this, thrust by weight equal to CD by CL, right? So let's keep that as such. And what else is given? So let's divide this thrust and weight. So what do I have is thrust is 4,000 divided by 30,000. That is basically your CD by CL. And if you divide this, you'll get as 0.133. Okay. So from here, I can say that CD equal to 0.133 CL. Right. Okay. From the drag polar, what is the given drag polar? It is 0.015 plus 0.024 CL square. Right? So which means substitute this CD over here, you will have what? 0.133 CL equal to 0.015 plus 0.024 CL square. So let's bring this here to this side so that we have a quadratic equation. 0.024 CL square minus 0.133 CL plus 0.015 is equal to 0, right? So which means if I solve the quadratic equation, now I'll have two values in, okay? So which means I'll have a CL is equal to 5.42, comma 0.1. So these are the two values that upon solving this quadratic equation. So from here, let's get the velocities for the corresponding thing. So if you use the velocity v equal to under root of 2w by rho s cl, right? So which means I will get the velocities as 17.3 comma and 116.64, okay, correspondingly in meter per second. So which means this has to be the mind you, if you solve this, you will be tempted to option give answer to the option D, okay? But beware, this is the minimum speed, right? And this is the maximum. So maximum is fine. But if you go back to the previous problem that we solved, because it's a common data question, right? Go back to the previous question and you see that the stall speed is 34.21, right? But let me rewrite that down in here. So my stall speed is 34.21 meter per second. But your minimum speed here is 17.3, which is impractical, right? Your stall speed is the minimum speed, right? So which means in this case, your stall speed is the minimum speed and this value is the maximum speed, okay? So hope you guys don't have any confusion in this, right? So which is my option C. Understood, everyone? Okay, so the reason is because stall speed is the minimum speed of the aircraft, and hence it has to be the minimum speed. If you get a value below the stall speed, then that is not a practical value. Okay, hope you guys understood this, right? Again, this is a very important problem. And problems like this, that help you apply concepts to this are a lot in number. Okay, in GATE. Okay, so please prepare for it. Last two questions. Okay, so if no doubts, let me go ahead then. So take this. So again, it's again from aerodynamics, but let's do that again. So circulation theory of lift is assumed for a thin symmetric airfoil at an angle of attack alpha. The free stream velocity is u. If the circulation at the quarter chord C by 4 of the airfoil is gamma 1, then the normal velocity is 0 at dash. So just give me a second. I think I made some mistake. Okay, fine. Let's do this. So circulation theory of lift is assumed for a thin symmetric airfoil at an angle of attack alpha. The free stream velocity is u. The circulation at a quarter chord of the airfoil is gamma 1. Then the normal velocity is 0 at dash. Okay. So let's do this. So we have an airfoil. Say he says that uh, lift at an angle of attack. So which means my CL is, you have to use this result 2 pi alpha. Now he says that if the circulation at the quarter chord is gamma 1, okay, so just let's say gamma 1, okay, so let's say that's the value of circulation, then the normal velocity is 0 at which location? So we have, so let's mark some points in here, right? So which means if you go back in here, normal velocity is basically this one, okay, so the circulation, what does this do is, it will, if I try to draw a flow field pattern, let's say let this be the singularity, so before this you will have kind of an upwash flow, if I draw the streamline patterns like this, and across this, you'll have a downwash pattern which is resembling something like this. So there is this singularity, we know, if you have studied the potential theory, from aerodynamics, so we know that across at the center point, your velocity blows off. Basically, if you go back to the equation, v is equal to gamma by 2 pi r, so which means you have an infinite velocity, right? This comes from the potential theory, right? So now you see, if I go back, so if I it basically increases from the exponent infinity, right? So the normal velocity has to be 0 at what point? So I have 4 points in here, right? C by 4, which is, if you see in here, there is, you have a velocity on which is in this direction, and on at the same point you have velocity in this direction as well, right? So which means you have the directions, they basically are equal and opposite, right? So which means these vectors has to cancel out, right? So my answer has to be C by 4, right? If you take C by 2, what happens is, let's take C by 2 first. C by 2 is, let's mark it somewhere in here. At some finite value, you see there exists some finite value of the velocity, correct? Which means, again, at c by 2 you have some velocity which is gamma by 2 pi r, right? So you have some finite value. At this center you will have both upward component as the downward component. Magnitude wise, the velocity blows off, whereas if you take the vector addition of these two velocity vectors, it drops to 0, right? So hence your answer has to be c by 4. Okay, hope you guys understood this, right? So if no doubts, then let me go ahead to the last question. A second identical airfoil is placed behind the first at a distance of c by 2 from the trailing edge of the first. The second airfoil has unknown circulation gamma 2 placed at its quarter chord. The normal velocity becomes 0 at the same chord-wise location of the respective airfoils as the previous question. The values of gamma 1 and gamma 2 are respectively. So again, this is a pretty tricky problem. So let's draw this. A second identical airfoil is placed. Let's draw that first. So we have at a distance of c by 2 from the trailing edge of the first. It says that second alpha is unknown circulation gamma 2 placed at its quadricard point. So this is C. So again, this is also C because he says second identical, right? So which means this will also has to be C. Okay, right. Let's go back to the question. It has an unknown circulation gamma 2 placed at its quadricard. The normal velocity becomes zero at the same chordwise location of the respective airfoils as in the previous question. The values of gamma and gamma 2 respectively. Okay. Okay. So from our previous question, we saw that your values of normal velocity were dropping off at this point. It's not gamma by 4, mind you, excuse me. So at this value, our velocity is 0. So let's say the velocity is 0 in here. The velocity is 0. Right? Let this be gamma 1 and gamma 2. Right? So if I try to draw the flow stream pattern again, it will be something like this. And whereas for this case, again, this downwash component of this airfoil, now this will see an upwash thing again, right? Let's mark something like this here. This is how the flow field behaves in this thing, right? Okay. So which means at this point, again you will have some cancellation, of the circulations because the circulation at this end. Let's mark some distance over here. Circulation produced by this end, where the velocity vector is like this, is counteracted by the velocity, which produces in this way, right? So which means if I determine that value, point at which this equals, which means the magnitudes of velocity has to be zero at this point. So let's do that first. So let's assume a point x from this c by 4. Okay. So I can write. Let's assume point x at which the normal velocity is zero, right? Normal velocity is equal and opposite. Okay, that's what you'll write. So which means I can say this as I can write gamma 1 by the velocity expression from potential flow theory is basically 2 pi x. This is equal to what? Gamma 2 by, say, if the whole distance is, so we are measuring it from this quadricard, right? So this is placed at c by 4, right? C by 4, and you have a c by 2 and you have a 3c by 4. Okay, so let me just draw it in a line. Let's assume this is the point somewhere, So this is c by 4. This is 3c by 4. And let me just redraw it again. So let's mark circulations. Gamma 1, gamma 2. Okay. So there is this straight line, let's assume, for instance. So from here to here, it is c by 4. From here to here, let's say this is the trailing edge. So this is 3c by 4. From here to the leading edge, it is c by 2. From here to here, it is again c by 4. From here to here, it is 3c by 4, right? So what I'm saying is from, let's mark some point in here. The distance is x basically. So it means from this to this, so how can you just write down the distance, right? So the velocity at this point will be induced what? So it is basically, I can write this as c by 4, this distance. I mean, watch carefully. So I can write this as c by 4 plus 3c by 4 plus c by 2 minus x, correct? That's what I can write over here, right? Because yeah, this distance is what is unknown, right? If this distance from this is x, so this has to be something minus x, right? So that turns out to be c by 4 plus c by 2 minus plus 3c by 4 minus x, right? So which means minus x will give out this distance, and hence you'll get that. Right? So c by 4 plus 3c by 4 is c, plus c by 2 is 3c by 2 minus x. Okay, so which means I will have a formula of 3c by 2 minus x times, you will have a 2 pi. So it means if I cancel out those two things, so gamma 1 by x is equal to gamma 2 by 3c by 2 minus x. Okay, let that be your first equation, right? Now, what else is given in the question? He's saying the normal velocities become zero at the same chordwise locations of the respective airfoils as in the previous question. And we also have, okay, let's try to do this. Just give me a minute, guys. I'm just trying to look at this. Because aerodynamics, I think I studied long back, so I'm just trying to work it out. Just bear with me for a moment. Okay, guys, I think this is I think a bit lengthy one, so never mind. So what I will do is, I will just type the solution in the chat box. Once the solution is being prepared, so that you can just come back to the video and then refer the steps. Okay, right, fine, guys. Okay. So with this, we wrap up today's session, and I know it's been hard, for me to do this. Being out of touch with aerodynamics for what 3.5 years. So, but thank you for literally cooperating with me. Because you guys were really cooperative in this problem, in these two problems. Right? And I hope you got the best out of the sessions today. And please subscribe to our channel. And if you have any doubts, you are free to put it in the chat box, or else the session is over. And for the last question, I will put it in the chat box. Okay, the steps. Okay, type it and put it. Okay, you don't have to worry about the solutions. Okay, guys. So thank you and have a good day.